Hey there, ladies and gentlemen, boys and girls. Today is kind of part two of our discussion about population growth curves. Today, we're going to just talk about how to calculate some of these things here. We need to figure out a little bit of how to calculate exponential growth curves and the growth in a population using logistical, which includes the carrying capacity. All right, so now I will say, just kind of preface this just a little bit here, is these type of growth curves are um, they look a little complicated, and because new math equations that are just kind of thrown on you can be kind of complicated. But just like a lot of things we've done in this class with biology, with math, just think about what you have, think of what you're trying to find, and then just use your algebra skills, which I have confidence that you have. All right, even if you feel like you're bad at math, like you can do multiplication and division. All right. So I'm going to use the whiteboard to kind of walk through some of those. And oh man, this quarantine is my hair is getting so long. I look anyway. Sorry. Let's go ahead and get started. So let's talk about exponential and logistical growth curves. All right. So let's talk about the logistical one. So the whole exponential. The whole idea is about trying to see the change in population size, right? And so we have a calculation that includes that growth rate. So this is what the equation looks like. I'll break it down and then we'll compare it to the logistical one. All right. So that's our equation. You're like, what? It's not that bad. All right. So first things first. All right. N means population size. All right. That triangle there is the Greek letter delta, which means change in. So here we have a change in population size. All right. So we have our change in population here. Now, the change in population, a lot of times that's what we're trying to calculate. All right, we're trying to see how do all these factors affect how much the population grows. And if it's exponential growth, it's probably a big number. All right, a big change. All right, so this includes not only, this is actually, what was the final population size minus the initial population size, the change in it. All right, this one here is delta t, which you might be able to guess pretty quickly is, especially from physical science, this is a change in time. So this left half of the equation here is literally just what is the change in the population in a certain amount of time? How much does the population change in the last 10 years? Right, that's what we're trying to see with growth rate, is how much has the population changed over a certain amount of time. All right. Let's go to this last part right here first. All right. So this is in statistics and math. This is called n, and then that little zero is not. All right, and not, which is basically just means start. All right, this is our initial population size. Just going to abbreviate like that for myself. All right, this is our initial population size. How much did we start at? And then we're going to see how much we changed over time. And what really is going to impact that, right, is this one right here. So much so I'm going to do it in a different color, and that's this right here, little r. That is growth rate. Which we did in the last video. We talked about those impacts on a population. Yeah, I'm not redoing this video. You're just going to have to live with that sneeze. All right. Growth rate is dependent on the natality and the mortality rate. How many are born versus how many are dying. All right. So growth rate, which we represent with R, little r, is basically the natality rate minus mortality. So in the last 10 years, 200 babies were born, only 50 individuals died. That's a huge growth rate. That'd be a growth rate of 150 individuals, right? The net of how many were born versus how many died, and that's our growth rate. So if we have a positive growth rate, we would expect a positive growth in the because if you have 200 individuals and a growth rate of 150 individuals every year for 10 years, that's going to be a big number. All right. If we have the growth rate as a negative number, that means the population is decreasing, because that means the mortality rate is greater than the natality rate, the birth rate. Death rate bigger than the birth rate. And if that's the case, then if you have more individuals dying than being born, you're not supplementing your population, and you are shrinking in size. All right. So that's all exponential growth. Remember, that's just that big curve up. All right. So now what happens when eventually we talked about that's exponential curve, but eventually you kind of start leveling off. You start leveling off. And when you start to level off a little bit, that's when we start to what we call logistical growth curve, because we're including carrying capacity. And it's actually very similar. It's pretty much the same equation, except we're including one extra aspect. All right, and that's that carrying capacity here. All right, so hopefully I gave myself enough room here. Give myself a little divider there. So it's the change in population over a change in time times is equal to the growth rate times the initial growth or initial population. And it's this last part here that we're adding to it. All right. And that is my daughter just woke up. I think I was being too loud. Come on down, Lorelai. Apologies. All right, so I'll kind of wrap this up because this actually we're almost at the end here. All right, this last part right here is the big part that we're at. We only do this one when we know we have logistical curve, because we included K. And K is the carrying capacity. So if we know the carrying capacity is 1,000 individuals, we have to include that. And in this case, N, this N right here, notice it's not, it's just a change. This is our current, the population at our population size at the moment. All right, so now we're including the population size and seeing how, or the carrying capacity, and see how that affects the growth of the population. Otherwise, I mean, first of all, you have to identify if we're asking for potential, or sorry, wrong class, exponential or logistical curve when you're going to a problem. And then you need to identify, because that depends which calculations, then identify what you have, and then the rest is kind of plug and chug. I'm not looking to make math complicated in this aspect. Right? I'm not trying to make complicated math problems on this. It's more about identifying, okay, what are they giving us, and where do I put that into the equation to help me figure out some numbers here. If you become an environmental scientist or a population scientist, you basically start doing these calculations in your head. All right. But otherwise, this is just kind of the basics, talking about what's growth rate, right? Natality and mortality, talk about population size and change. And then with logistical curves, because you have that flattening off at the carrying capacity, we have to include the carrying capacity at that, right? I realize I just wrote carry capacity, not carrying capacity, but Po Buddy's nerfect. Sorry, once again, to interrupt. I need to make a quick correction. It just wouldn't be a Mr. Richardson lecture unless he made a mistake during it. Except the only difference is I don't have you guys to call me out on it or yell at me or, all the good stuff. So I apologize for any background crunching noises. That's just my daughter eating breakfast right behind my computer. So it's going to be crunchy. All right, sorry, real quick. In our logistical curve calculation, to my shame, that N should be a K. That's it. Many apologies, and back to our regular scheduled programming. All right. Otherwise, if you have any questions, honestly, you could probably Google like 15 people walking through these problems and stuff like that. It's mostly just kind of plug and check. I'll probably put in a supplemental video on how to, walk through some of these problems. But if you have any questions, don't hesitate to ask. Otherwise, good luck, and may the science be with you. Bye.